The signature prefix value V and public key recovery. As mentioned in the structure of a transaction section, the transaction message doesn't include a from field. That's because the originator's public key can be computed directly from the ECDSA signature. Once you have the public key, you can compute the address easily. The process of recovering the signer's public key is called public key recovery. Given the values R and S that were computed in the ECDSA math section, we can compute two possible public keys. First, we compute two elliptic curve points, big R and big R prime, from the x-coordinate R value that is in the signature. There are 2 points because the elliptic curve is symmetric across the x-axis, so that for any value x, there are two possible values that fit the curve, one on each side of the x-axis. From R, we also calculate R inverse, which is the multiplicative inverse of R. Finally, we calculate Z, which is the n lowest bit of the message hash, where n is the order of the elliptic curve. The two possible public keys are then K1 equals to R inverse times the quantity small s times big R minus small z times big G, and K2 equals R inverse times the quantity s times big R prime minus z times big G, where K1 and K2 are the two possibilities for the signer's public key. R1 is the multiplicative inverse of the signature's R value. S is the signature's value. Big R and big R prime are the two possibilities for the ephemeral public key, big Q. Z is the n lowest bits of the message hash, and big G is the elliptic curve generator point. To make things more efficient, the transaction signature includes a prefix value V, which tells us which of the two possible big R values is the ephemeral public key. If V is even, then big R is the correct value. If V is odd, then it is big R prime. That way, we need to calculate only one value of big R and only one value for big K. Separating signing and transmission. Offline signing. Once a transaction is signed, it is ready to transmit to the Ethereum network. The three steps of creating, signing, and broadcasting a transaction normally happen as a single operation. For example, using web3.eth.send transaction. However, as you saw in the raw transaction creation and signing section, you can create and sign the transaction in two separate steps. Once you have a signed transaction, you can then transmit it using web3.eth.send signed transaction, which takes a hex encoded and signed transaction and transmits it on the Ethereum network. Why would you want to separate the signing and transmission of transactions? The most common reason is security. The computer that signs a transaction must have unlocked private keys loaded in memory. The computer that does the transmitting must be connected to the internet and be running an Ethereum client. If these two functions are on one computer, then you have private keys on an online system, which is quite dangerous. Separating the functions of signing and transmitting and performing them on different machines, on an offline and on an online device respectively, is called offline signing and is a common security practice. The offline signing of Ethereum transactions diagram shows the process. 1. Create an unsigned transaction on the online computer where the current state of the account, notably the current nonce and funds available, can be retrieved. 2. Transfer the unsigned transaction to an air-gapped offline device for transaction signing, for example, via a QR code or USB flash drive. 3. Transmit the signed transaction back to an online device for broadcast on the Ethereum network, for example, via QR code or USB flash drive. Depending on the level of security you need, your offline signing computer can have varying degree of separation from the online computer, ranging from an isolated and firewalled subnet to a completely offline system known as an air-gapped system. In an air-gapped system, there is no network connectivity at all. The computer is separated from the online environment by a gap of air. To sign transactions, you transfer them to and from the air-gapped computer using data storage media, or a webcam and QR code. Of course, this means you must manually transfer every transaction you want signed, and this doesn't scale. While not many environments can utilize a fully air-gapped system, even a small degree of isolation has significant security benefits. For example, an isolated subnet with a firewall that only allows a message queue protocols through can offer a much reduced attack surface and much higher security than signing on the online system. Many companies use a protocol such as 0MQ for this purpose. With a setup like that, transactions are serialized and queued for signing. The queuing protocol transmits the serialized message to the signing computer in a way similar to a TCP socket. The signing computer reads the serialized transactions from the queue carefully, applies a signature with the appropriate key, and places them on an outgoing queue. The outgoing queue transmits the signed transactions to a computer with an Ethereum client that dequeues them and transmits them. Transaction propagation. The Ethereum network uses a flood routing protocol. Each Ethereum client acts as a node in a peer-to-peer network, which forms a mesh network. No network node is special. They all act as equal peers. We will use the term node to refer to an Ethereum client that is connected to and participates in the P2P network. Transaction propagation starts with the originating Ethereum node creating a signed transaction. The transaction is validated and then transmitted to all the other Ethereum nodes that are directly connected to the originating node. On average, each Ethereum node maintains connection to at least 13 other nodes called its neighbors. Each neighbor node validates the transaction as soon as they receive it. If they agree that it is valid, they store a copy and propagate it to all their neighbors, except the one it came from. As a result, the transaction ripples outwards from the originating node, flooding across the network until all nodes in the network have a copy of the transaction. Nodes can filter the messages they propagate, but the default is to propagate all valid transaction messages they receive. Within just a few seconds, an Ethereum transaction propagates to all the Ethereum nodes around the globe. From the perspective of each node, it is not possible to discern the origin of the transaction. The neighbor that sent it to the node may be the originator of the transaction, or may have received it from one of its neighbors. To be able to track the origins of the transactions, or interfere with propagation, an attacker would have to control a significant percentage of all nodes. This is part of the security and privacy design of P2P networks, especially as applied to blockchain networks. Recording on the blockchain. While all the nodes in Ethereum are equal peers, some of them are operated by miners and are feeding transactions to blocks to mining farms, which are computers with high-performance graphics processing units, GPUs. The mining computers add transactions to a candidate block and attempt to find a proof of work that makes the candidate block valid. We will discuss this in more detail in the consensus section. Without going into too much detail, valid transactions will eventually be included in a block of transactions and thus recorded in the Ethereum blockchain. Once mined into a block, transactions also modify the state of the Ethereum singleton, either by modifying the balance of an account in the case of a simple payment, or by invoking contracts that change their internal state. These changes are recorded alongside the transaction in the form of a transaction receipt, which may also include events. We will examine all this in much more detail in the EVM chapter. A transaction that has completed its journey from creation through signing by an EOA, propagation, and finally mining has changed the state of the singleton and left an indelible mark on the blockchain. Multiple signature transactions. If you are familiar with Bitcoin's scripting capabilities, you know that it is possible to create a Bitcoin multi-sig account, which can only spend funds when multiple parties sign the transaction. For example, 2 of 2 or 3 of 4 signatures. Ethereum's basic EOA value transactions have no provisions for multiple signatures. However, arbitrary signing restrictions can be enforced by smart contracts with any conditions you can think of to handle the transfer of Ether and tokens alike. To take advantage of this capability, Ether has to be transferred to a wallet contract that is programmed with the spending rules desired, such as multi-signature requirements or spending limits, or combinations of the two. The wallet contract then sends the funds when prompted by an authorized EOA once the spending conditions have been satisfied. For example, to protect your Ether under a multi-sig condition, transfer the Ether to a multi-sig contract. Whenever you want to send funds to another account, all the required users will need to send transactions to the contract using a regular wallet app, effectively authorizing the contract to perform the final transaction. These contracts can also be designed to require multiple signatures before executing local code or to trigger other contracts. The security of the scheme is ultimately determined by the multi-sig contract code. The ability to implement multi-signature transactions as a smart contract demonstrates the flexibility of Ethereum. However, it is a double-edged sword, as the extra flexibility can lead to bugs that undermine the security of multi-signature schemes. There are in fact a number of proposals to create a multi-signature command in the EVM that removes the need for smart contracts, at least for the simple M of N multi-signature schemes. This would be equivalent to Bitcoin's multi-signature system, which is part of the core consensus rules and has proven to be robust and secure. Conclusions. Transactions are the starting point of every activity in the Ethereum system. Transactions are the inputs that cause the Ethereum virtual machine to evaluate contracts, update balances, and more generally, modify the state of the Ethereum blockchain. Next, we will work with smart contracts in a lot more detail and learn how to program in the Solidity contract-oriented language.